Hello, welcome to a video about significant figures. The word significant can be a little bit confusing potentially, so we're just going to talk about what makes a digit significant and what makes it not significant, and hopefully we'll get you all settled so when you come into class we can hit the ground running with some calculations. Physicist Patrick Lynn is credited as referring to this topic as boring but important. So I can't make it much less boring, but it is nevertheless important. So we're going to go through some rules to help you discern the value and the reliability of measurements that we're going to make in lecture and in lab. The purpose of trying to figure out whether or not significant figures or figures are significant or not is to keep track of the quality of a measurement. So if we want to convey a number, it's important that we understand the reliability inherent in that number that we've expressed. So this really comes down not to the math of it all, like math is math and that doesn't change, but it's when we start showing our final answers that we want to show them in a way so that other scientists understand how reliable our numbers are. Right? This is going to also, in part 2, I'm going to have a really short video showing you how to think about propagating that error or that uncertainty in calculations. So we're going to take these numbers, plug them into formulas, do some math, and we still have to keep track of the variability or the reliability of our numbers. Okay, so let's imagine a simple scenario where we put this weird green liquid on a scale, and that scale tells us that we have 95.85 grams of that liquid. That's the scale telling us its most reliable measurement for that particular piece of matter. So when we report that number, we can write it down as 95.85. That's what the scale tells us. We would not want to write that down as 95.85000000. Those two numbers are mathematically the same. I think we can all agree. If we can't, then you should equilibrate yourself there, calibrate yourself, and make sure you understand that those two numbers are mathematically the same. But what they're saying to scientists is really different. The bottom number is saying that we are really sure about the reliability of this number to like the 8th decimal place. Right? And the top number is saying we're really only sure about the first 2 decimals. Anything after that we really have no idea about. So when we show all these extra zeros, we're communicating to the scientific community that we are really certain. We have a high certainty of this measurement. That's not true, right? The scale's only telling us it's 95.85, so I can only report that top number. So by not putting numbers, I'm conveying my limited amount of certainty. So we only want to show the numbers that we have measured with some certainty so that we can convey the reliability of our measurement. I would not show the number as 96 because then I've taken away some certainty. There's no reason to take away things that we're really certain about. We also don't want to overstate the reliability of a number. So we're going to start practicing looking at numbers and figuring out how reliable they are, and we do that by counting significant figures. So the more significant figures in a value, the more certainty there is in that value. So we got to practice that skill. Okay, so we have to understand when we look at a number which digits are conveying certainty and which digits are just placeholders. Both jobs are really important. So it's really weird when we call some digits significant figures and other digits not significant figures. They're all significant according to the English definition of the word significant. It's just that when we talk about it in chemistry, a number is either significant, meaning it's conveying certainty, or it's a placeholder, or we would call it not a significant figure. So, it's just new language that we have to get used to talking about. All right, so if we look at the number 12.34, right, these are all non-zero digits. Before the decimal, after the decimal, doesn't matter. Any number that's not a zero is conveying certainty. So this is just like the scale that we just saw. There are 12 in the whole number, 0.34 in the decimal. All of them are conveying certainty. In the next number, I want to point out this 0 and any 0 that comes before the decimal is just telling us that there's nothing in the whole number places. So there are no whole numbers. Right? We only have a number less than 1. That's all that 0 is telling us. It's neither a placeholder really, nor is it conveying certainty. It's just telling us a decimal's coming. So if we look at this value, then all 4 of these digits are conveying certainty. Now if we look at 12,340, right? The first digits are conveying certainty. That last 0 is not telling us that we're certain about that position. It's just telling us that we are holding that place. So this is just holding the size of the number. It's not conveying any mathematical importance. This is just a placeholder. Right? So when we look at the other number, the last number on the sheet, we can see that we can also hold places after a decimal. So we don't have to just hold places at the end of a whole number. So if we look over here, these two zeros, they're just saying that our number is really small, right? They're saying wait for it. You didn't even start measuring anything because your number is so little until you get to the third decimal place. So these are, again, placeholders up front, and we're conveying the certainty of our measurement at the end of that number. So that's the way we have to start to think about where these zeros play out. And the next slide is going to show some rules that are going to help us understand. So I can arbitrarily look at a number and say if something's significant or not, but you're going to need to follow the rules to ask yourself these 3 questions, right, to look for numbers to see if they're placeholders or if they're significant. The first rule is really easy. All non-zero digits express certainty about a measurement. So if I say something's 6.13 grams, that's 3 numbers that are all significant. That's 3 significant figures. 1,345, all non-zero digits, 4 significant numbers. 0.966, again, that 0, I could take it or leave it. It's good to show it. It's just telling me a decimal's coming. That's 3 significant figures. Okay, all trapped zeros. So we have to kind of figure out what a trapped zero is, but they're going to be conveying certainty about a measurement. That means they'll be significant. So if I look at this number, the 1 is significant up front because of rule 1. The 2 at the end is significant. So if I feel really good, if this is a very reliable number here, right? Ooh, If this is a very reliable number, and this is a reliable number because of rule 1, then these have to be reliable numbers. They're just trapped in between. So any zero that happens between 2 significant digits are also significant. So this would be 5 significant figures. Right? Same is true here. Doesn't matter where that decimal happens. If you have a significant digit and you have a significant digit, this guy's trapped. So he would be 3 significant figures. Doesn't matter how many trapped zeros there are. We see the 0 between the 3 and 4. We see the 2 zeros between the 4 and 6. All of these digits are significant. So that would be 7 significant digits. The last rule is the one that's a little bit crazy. Both parts of this rule have to be true. Zeros that are after the decimal and at the end of the number, both have to be true. Those are significant digits that express certainty about a measurement. So let's see what that looks like. If I look at this number, 0.2300, this is mathematically the same as 0.23, right? No difference mathematically between these two values, but this value is a more reliable value. This value is making a claim that there is nothing in the thousandths place, right, or the 10,000ths place. This guy is more reliable because we see those zeros at the end. So because they're at the end of the number, right, check, and because they are after the decimal, check, then this rule 3 applies. These guys are adding significance to the answer. This is more reliable than that. This has 4 sig figs. This has 4 sig figs, and this only has 2 sig figs. Right? So that's how we can use these extra significant zeros to add certainty or reliability to our value. Same with whole numbers. If we have a 0 that's after the decimal at the end of the number, this would be 4 sig figs. So I'm really certain about that value. It has high reliability. If I were to say 360, right? Well, now I've got a placeholder 0. He is not significant, and I have 2 significant figures here in the hundreds and tens place. That would just be 2 significant figures. So by adding that decimal and adding an additional 0, we've added 2 places of significance. Again, you know, it could be a larger number. That 0 could be at the end of a value, but it's got to be after the decimal, at the end, the very end of a number. That's where we can tag on zeros that are not placeholders. Right? These zeros are not placeholders. These are significant zeros. So we just have to make sure that when we're evaluating zeros, we either know that they're trapped, we know that they apply to this very specific rule, or if none of those things are true, then they're probably placeholder zeros. Placeholder zeros are important, but they are not significant. They're not adding reliability to a measurement. So if we look over here, we've got these 3 zeros. They are after the decimal. That's looking good, but they are not at the end of the number, right? We didn't tag them onto the end, so they're not significant. They do not follow the significant rules. These are placeholders. So if you were to evaluate this number for certainty or reliability, you could say that this would have three significant figures, right? And that's it, because these are just placeholders. Likewise, down here, these are placeholders, right? They are at the end of the number, but they are not behind the decimal. So that would be 11,000, and this would just, for the sake of certainty or reliability, this would have 2 significant figures. 30, same deal. He is at the end of the number, but he is not behind a decimal. He is holding the ones place. He is not adding certainty to our measurement, so this is 1 significant figure. Okay, so those are the rules. We're going to practice them in class, and every number that we create, you're going to have to be able to look at it and determine how many significant places are being reported, and we'll use those rules in the second part of this video to use them in calculations. All right, see you guys then.